Hello friends, my name is Derek Harder, and in this video we're going to continue talking about some of the mathematical building blocks of neural networks. And in particular, we're going to be continuing with looking at data representations for neural networks. So in our previous example, we started with some data stored in multidimensional NumPy arrays. Okay, so in mathematics, a multidimensional array is simply known as a tensor nowadays. Okay, so a tensor could be like a one-dimensional vector or a two-dimensional matrix or a higher dimensional array. Right, so that's all a tensor is. So in general, all current machine learning systems use tensors as their basic data structure. And that's kind of what the name TensorFlow, that's what it's named after. It's really a library for managing and manipulating these tensors. So at its core, a tensor is just a container of data, usually numerical data. Almost exclusively, it'll be just numbers in our tensors that we use for this class. So and it can have multiple dimensions: rank 1, rank 2, rank 3, and so on. Okay. So let me go ahead and restart this notebook here. So in general, all current machine learning systems and libraries use tensors as their basic data structure. So if you're not familiar with using NumPy, I really would recommend going back and reviewing NumPy and some of the advanced slicing and other techniques for NumPy. So I should have resources for you in this course for doing that. So, but really, like NumPy, TensorFlow tensors are really just a data structure for representing, holding an n-dimensional array of numerical values. So, for example, the simplest, in essence, you can think of something that has no dimensions, 0 dimensions, as a scalar. Okay, so when you hear me use the term scalar, that simply means what you normally think of as a variable with a single value. So here you can create scalars in NumPy array. We're going to be using NumPy for all these first examples here. So if you just give it a single number, you actually end up with a scalar value, a NumPy array with 0 dimensions. Right? So vectors and matrices are common in mathematics. So and we'll be using vectors and matrices a lot in this class. So a vector is really just a matrix with just a single dimension. Right, so if you create a NumPy array with just a list of values, it will create the array with 1 dimension. So there's a little bit of confusion about talking about the dimensionality of a tensor. So in some contexts, you will see people refer to this as a 4-dimensional vector because there's 4 values in it. And we can use this to represent a point in 4-dimensional space. Okay? But in general, in this class, we'll usually when we're talking about dimensions, we will talk about the dimensionality of our representation space, but like here, we would consider X to be a 1-dimensional tensor, which is another name for that is a vector. 2-dimensional matrices are how we normally represent data to do machine learning with. So a matrix or a 2-dimensional tensor has rows and columns. That's the way we normally think of it. So the number of dimensions is 2. In this case, we've got 3 rows and 5 columns. So that's what the shape of this is. Okay? So almost always by convention, the row dimension, which is the first dimension, is going to be how we index the samples. And then for a table like this, a matrix, the columns represent the different features for that sample in machine learning. So we will be doing a lot of stuff. We'll see some more examples with higher dimensional tensors. So rank 3 or higher tensors don't normally have special names like a vector or matrix, right? They're just high dimensional. They're 3-dimensional tensors, 4-dimensional tensors, or n-dimensional tensors. So in this case, we create a 3-dimensional tensor. So notice when you print it out, it has 3 dimensions. It's a 3 by 3 by 5 is the shape. And you'll get it displayed. So for higher dimensional things, it has to, each one of these kind of represents like a slice, a 2-dimensional slice in the 3 dimension of the tensor. Okay. And if you pack together some 3-dimensional tensors, you get a 4-dimensional tensor, and you can keep going like that. So a tensor is defined by 3 attributes: the number of axes that it has. That's really, it's what in this class that's what we would call the dimension, the number of axes or the number of dimensions. The shape. So if I have 3 dimensions, each dimension has a certain count of the number of items that are along that shape. NumPy and the TensorFlow library represent that as a tuple of integers. And then the data type. So we will exclusively be working with numerical data type for the most part in this class. So the data type will usually be integers or floats in our tensors, in our high dimensional arrays. So we touched on this in the previous video a little bit, right? We looked at the MNIST data set. So when we loaded it, it loaded in as a NumPy array that was 3-dimensional. And the shape was for the training data was we had 60,000 in the first dimension, which is usually going to be the sample dimension, and then we had 2 other dimensions, which were the row and column of our pixel images. We had 28 pixels, 28 rows of pixels, and 28 columns of pixels in these images. And as originally loaded, the data type was unsigned int, although we converted those to float values, so we converted those grayscale values from integers to floats in our previous video. So we can see with that, the image number, I just picked the 4th image out of there. So this is what the actual, so here, we'll do this a lot. So if we're slicing a NumPy array or a TensorFlow tensor, if you just specify the first dimension, you're going to be getting 1 sample out of that. And since that 1 sample, image number 4, or index number 4 in our tensor here, is a 28 by 28 pixel array, if we pass that to the IM show, it knows how to display that as like a grayscale. So so notice we didn't specify the slice for all 3 dimensions in that previous one. If you don't specify a dimension on a slice, it will assume you want all the values in the unspecified dimensions on a slice. Okay. So we can use that, for example, for doing batch training. So we'll talk about what batch training for gradient descent is in a bit in this class. So, for example, if we want to get the samples from 10 to 100, we can slice something like this on our train images. So this will get samples 10 to 100. Okay. And it's equivalent to doing something like that. So we're explicitly specifying the other 2 dimensions, but by using the empty colon, the syntax means I want all the values. I don't want to have just a sub portion of the values in the index 1 or the index 2. Okay. So notice what we get is we get a or we can be explicit. So we get a slice of 90 samples. Each one of the samples has the full 28 by 28 pixels. But if we want to, for example, we can get the middle of an image. So here we're actually getting the middle. We're getting the lower right-hand corner. So we're getting the pixels from 14 to 28 of the rows and the pixels of 14 from 28 to the column. Or here we get the middle of the port of the image. So this gets the pixels from 7 to -7. So from 7 to 14 rows and 7 to 14 columns. But again, I'll mention you should be, you can slice the same way for most of these kinds of tensor libraries. So you can do the same kinds of slicing with TensorFlow tensors as well. So you should be comfortable with this notation, what it means. So by convention, the first axis in all tensors for machine learning is going to be the sample axis. So if I need to sample a batch of items to, for example, do training with, I can just slice on the first index. So same as what we did before, right? So if I want a batch size of 128 samples for our training images, I could do something like that to get the first 128 images. The second batch then, so just by manipulating this index, if I keep a track of where I'm at, I can get my next 128 images by slicing on the sample index like this. All right, so then moving on just a little bit, our textbook gave a few examples of some real-world examples of data tensors. We'll be using some of these in this class here. So the most common case is really vector data. So in that case, you're going to end up with a rank 2 tensor, so a 2-dimensional array. But the first axis is going to be the sample axis, and then the second axis is the feature axis. Okay, so the columns of this two-dimensional tensor, which is also called a matrix, represent different features of the dimension. Okay? So again, if you've taken a machine learning class, this should be fairly familiar. So here I'm pulling out the California housing data set from the Keras datasets library. So it actually has 8 columns and has 16,512 samples in this training data set. So if you go and look at the description of the columns and the link that I have here, you'll see that these represent things like the latitude and longitude of the house, and the number of people in each one of the samples, the average number of bedrooms, and other stuff like that. Right? So that's a basic structure for doing machine learning and for building like a logistic regression or some other machine learning. So again, we can pull out the sample at index 0, so you can see like this is the latitude and longitude, and then other measurements about the housing unit in this data on this first sample here, or the other columns of this vector. So another common data set that we'll be using in this class are time series data or sequence data. So in that case, normally you'll end up with having a 3-dimensional tensor. So you'll have 3 dimensions. So there'll be a sample dimension. I mean, for all these, the first dimension will always be for the sample. But then the second dimension is the time step. So you can kind of think of this, for example, like the example I was going to do, I haven't done it yet, is like if instead of for this California housing data, which was the data for the year 1985, I believe, or something like that, if I had collected data from 1960 to 1990, I would have a time series data, right? So I would show, in that case, I would want to have data so that for my sample 0, I want to know what the data was when I measured it in 1960. So the time step the index would become the year in my example if I was doing a measurement every year. So I could get all the samples 1960 to 1980 or whatever I said for that data set I'm making up by just getting sample 0. But if I want just the housing data for 1960, I would have to pick which location I want, which sample I want, and then which time steps, second index to get the time series index. Another common format that we're going to be using is image data. So we are going to be doing some image classification and doing some convolutional neural networks in this class. So our MNIST data set that we looked at already was image data, but normal image data is going to actually come out usually as a rank 4 or 4-dimensional tensor, right? That has the shapes, again, the first dimension 0 is going to be always the samples dimension, but then it has height and width like our MNIST data, right? So in this case, the CIFAR 10 data set is actually images that are 32 by 32 pixels. But then the fourth one is channels, because normally for our image data, we're going to be working with color images. So typically what we have is 3 color channels. So for each pixel, we've got 3 values, the red, green, and blue value. So that's what this channels dimension is on here. So and again, though, if we extract this out, we can use im and im show. It also knows how to handle color data. So we can use that color channel, the fourth one. So if we pull out the fourth image, the CIFAR data, it's like a vehicle. So the CIFAR data has things like vehicles, and I can't remember the categories, plants and tools and some other stuff like that. That's we're trying to categorize from the training here. All right, and then finally, you can imagine, I'm not certain if we'll be able to work with video data in this class. That takes definitely some processing power, and you probably need a NVIDIA a GPU to work with that, or some GPU. But as you can imagine, this is kind of a similar extension to like we did for the time series extension from the regular vector data for machine learning. So you can think of a video as a first approximation as a series of frames of images, right? So the normal convention then for video data is there's a sample and then there's another thing in there. This corresponds to like the time step for the time series data. So this is the frame number, starting with the first frame in the video, frame 0, frame 1, 2, 3, and so on. So frame number. Each frame is an image of some height and width, and usually we have color videos, so we've got a channel with the red, green, blue. But this gets really big really fast, right? So a quick calculation here, similar to what the textbook talked about, but if you wanted to do some training on a batch of 4 videos that each had 1,800 frames, so if we're sampling at 30 frames per second, and the video is 60 seconds in size, that would mean you'd have 1,800 frames in a 60-second video sampled at 30 frames per second. So that's our second dimension. And, you know, this is pretty small for a video image, but, you know, if we're using a relatively small compressed video image, 144 rows by 256 columns, and our 3 color channels. Okay, so that was just a quick example of the data representations. But to summarize some of that, you know, you should be relatively comfortable with using NumPy arrays and slicing. So we'll do the same things with tensor arrays, and that's how we usually represent data and pass it around. I guess some of the important things, you know, that last part is really will make it easier for you to understand. So in general, the array that we're using, or the tensor that we're using, the first index 0, is always going to be the sample index, and then the other indexes will be how we get the features or other parts of the feature. So especially for like a time series or a video, the second index, the index 1, is going to be the frame number or the time step number in that time series. All right, so that's it for the video. I hope you enjoyed it, and I hope you come back for the next one. I'll see you next time.